in the sense of deep neural networks, they don't like it, okay, because they are not, it's pretty modular, okay, independently optimized, okay. You actually can put, again, everything together with what people call end-to-end system, okay. You say, if I can run this thing as an end-to-end system, okay, I don't do frame classification and by-tree decoding, okay. If I can learn a system that directly do sequence decoding, okay, so that I can optimize my network to output a set of symbols. I know effectively it's doing proper frame classification and sequence sort of decoding. These two things have to be done simultaneously. Okay, so it's not just doing this learning, doing this learning and put them together into an HMI network. That's just we need a new framework, design a new loss, so that the new network can directly taking features in taking this sequence out directly, okay, within a single network. Okay, that's the end-to-end learning. So people start to go into that space. Okay, so we call it end-to-end learning. The first end-to-end learning is basically taking these two things combined. Okay, so again, repeat, we don't do DNN static model for frame classification and by-tree decoding to HMN. Okay, we say this is RNN based. Okay, the RNN is going to be trained with a specific loss called CTC loss. Okay, CTC loss, again, we don't have time to go into this, but they call it connectionist temporal classification. So they turn a sequence decoding problem into a sequence classification problem. Okay, so see the word classification. So basically, you directly take the feature in, you output directly a sequence of symbols. Okay, so it's a sequence out. Okay, so it's not recurring. It doesn't say, okay, I'm gonna look at what's happened in the past, output the next one, look at what's in the past, output the next one. Okay, it's designing a loss. Okay, that directly say, okay, I'm gonna look at this independent, they treat it almost independent sequence. The connection between we use the RN, okay, the RN is gonna output directly, okay, the phonetic sequences, okay, so this network can be trained directly, okay, to achieve we call it end-to-end. So we no longer say, okay, this frame is that state. Now look at that state, do a transition probably to find a by-tree decoding. We now say let's design a loss called connection temporalis loss. Okay, let's take the sequence and the sequence of this and sequence of the phonetic symbols. Okay, the media is RN based stuff. It could be LSTM, it could be anything. Okay, then learn this thing directly. Okay, then you can input a sequence of observation, directly output a sequence of phonetic symbols. Okay, so it breaks down the boundary between frame classification and the decoding, put it all together into a single network by rearrange the loss by thinking about the problem in terms of designing a new loss so that my recurrent network can directly output this kind of stuff. So that's the first thing people have started putting it into we call it end-to-end network. I want to skip this. I don't have time to go through this. Okay, so you can see that with LSTM HMN or LSTM CTC loss, okay, the word array with the bidirectional is starts to be the LSTM HMN loss. Okay, and people look at this result. Usually, people will start saying, okay, there's not much difference. Okay, but the good thing is with LSTM CTC loss, this is a lot, so there's no additional component. Okay, you only have an LSTM now. Okay, we feature in symbol element. With this, you have LSTM that will be run. Okay, give you the probability. You need to have an HMN, have a transition probability. You have by-tree decoding, all those things, right? So you have CPU running by-tree decoding. You have an LSTM that gives you the probability. You have this combine these two things and then give you the final output. This you have a single network structure. Okay, then you learn those network structure with a particular loss design. Okay, and once that loss is designed, then basically the input of sequence is the input of sequence out. Okay, that basically takes care of what we call the end-to-end structure. Okay. So again, end-to-end is always what deep learning kind of community likes because it can fully optimize what naturally we break them into logical steps. They can be can merge into one step. And when you merge into one step, the problem then becomes designing network architecture. Okay, the problem doesn't become which mathematical models I use. The network becomes which deep learning component I put together. Okay, so that I can achieve a good performance. Okay, so that's how first kind of end-to-end learning that shows. Okay, let's skip this thing. Yeah, you can do again deep networks and then do CDC loss and then you still within that you do recurrent or bidirectional neural network. Okay, in the beginning layers you usually do a 1 to 2D invariant convolution neural network. Within each you do a batch normalization, right? You see, when we start going to sort of deep learning stage, right? In the ASR pipeline, we put together frame classification and the Viterbi decoding put together now into a single network. We can do LST even to do input and output. If you can do LST, you can do other stuff, right? Here, what you do is basically you add very, many layers, 7 to 10 layers of bidirectional neural networks. You see a lot of trick, but the final is the fully connected layer. So, and then with the CDC loss. In the beginning, you add the convolution neural network because it helps you capture the local features. You don't do MFC anymore. You start by spectrogram. Convolution neural network helps you learn the filters. Bidirectional neural network helps you learn the sequence property, temporal sequence property of input and output. Finally, get an output, and then you do CDC loss. Do batch normalization because within the layers, okay, there are many layers. If you don't do batch normalization, it's very hard to converge. Okay, the feature value can be very small. So you start to have all these tricks of deep learning that brings into the speech community, and people try in the speech community say, okay, let's now start to design all different network architecture. Okay, now not to solve the DNN frame classification problem, now to solve directly the entire sequence in the entire cell. Okay, so that's end-to-end. Okay. Let's see. Okay. Now, as you can imagine, okay, through this entire pipeline, we start, feature extractor, frame classification, sequence model, have a dictionary, have a language model I try. Okay. DNN comes in first, swap this out. So okay, frame classification become DNN. Okay. They don't now you look at it and say, okay, but if I still have multiple components, put this thing together now becomes a CDC or a sequence model of some sort that learns directly. But you still have this point where you say, okay, I have now the sequence of phonetic symbols. I need to map into word. You still need a dictionary here. Now you have a language model that give me the distribution weighting of n-grams so that I have to reweight kind of sentences. Okay. So people don't like that. Okay, in terms of nowadays we have so much data, and people just say, okay, why modular? Okay, why component wise? Can we take this part to this part entirely into a single network? Okay, can I just have feature sequence in to a word sequence out? Okay, so if I can design a network architecture within all these things, I don't have to have intermediate model that does frame classification, sequence model, pronunciation model, or a lexicon, and then finally have a language model that's reweighting the things that I've done on things. So people have, again try to do these things, and then when this thing started, okay, this is about the time also when the attention starts, the attention mechanism in neural network becomes first introduced. Okay, so attention mechanism helps spark this process of doing speech to text directly. Okay, so you don't do phonetic prediction, then dictionary lookup, then word reweighting. You directly take the feature in and predict the character directly. Okay, so if you don't say a cat is pronounced as cat, okay, and then you have dictionary say, okay, that pronunciation equals CAT. Now you just say, okay, I have a feature in, I want each frame to predict whether it's C or A or T. Okay, it's directly going from acoustic signal to predict character. Okay, and that approach has been bundled together into a very complex sort of attention-based networking. Now, again, these things emerged, right? When the attention started, it was an attention mechanism. Okay, people use it in a sequence model. Okay, later, as we know, when you get multi-handed attention, okay, and then with a few tricks, those attention-based networks are people nowadays know transformer. So So attention is the when the transformer later could emerge into a transformer structure, and the transformer structure then becomes the basic de facto structure. Okay, in almost nowadays current state of the art AI systems to do anything. Okay, it's speech recognition, it's in computer vision, it's image processing, it's in everywhere. Okay, right? It's in natural language processing where you take a sequence you put in with multi-head attention and a single have a sequence of output out. So at this, when people start thinking about this problem about 3, 4, 5 years ago, and then they start building this thing. So if you don't know the actual HMM GMS system, if you start learning the state of the art of ASR system, you're not going to learn these things. Okay, what people will tell you is that there is a network. Okay, that links acoustic feature in, it could be spectrogram or anything. It gives you a character output. Okay, the actual rationale of the model now becoming that is because of this process of doing frame classification, sequence modeling, phonetic transcription, dictionary lookup, and word model probability. Now we just the current state-of-the-art model put everything together. Okay, into a single sort of a network architecture, and you just simply do that. So that's kind of I can imagine what very currently that's how the ASR community is looking at it. So skip this attention-based network. Okay, the first thing to compare with the CTC loss, people do find attention-based things better than CTC. I'm not going into detail of that, but again, it's a very nicely used framework that have attention that's gonna happen on every different layers. Okay, so I think let me see if I have more. Yes, okay. I think we'll end at this slide. Okay, the ASR system. Okay, in the entire course. Okay, we spend basically the first half of the course to teach feature extraction. Okay, again the features doing DSP into a sequence, and that's it. Okay, the second half of the course we say let's run an actual ASR system starting from here. Okay, so we say okay let's build an HMM GMS system. Okay, we inspired by the way everybody pronounce differently, so you have features that be probabilistic, you need to have duration that's also probabilistic. Okay, a good model is an HMM model, the Gaussian Mason all put together. You'll need a dictionary, somebody needs to hand it to you a dictionary. So if you're running your own ASR system now, you always have a dictionary in your file. Okay, think about in a real world case, if nobody gives you that dictionary, you are not going to be able to run any ASR in that case. So the dictionary is actually I think the most costly, also the most valuable in terms of statistical machine sort of a ASR. But once you have dictionary, you map the phonetic sequence into words. Okay, then you say okay, I use an N-gram model again to re-smooth. Okay, I'm trying to find the probability of this word given a past word. Okay, that probability again remodel. Then we teach N-gram model as an approach to do that. Okay, now let's construct the entire ASR pipeline that lays the foundations of all the modern ASR system. The things start to rapidly change when deep learning starts to appear. Okay, deep learning appears because they start to not work on particular mathematical models. What they work on is a particular loss function, right? So when you design a loss function, as long as they're differentiable, okay, now with proper tricks in deep learning, then you can make the model do classification or regression or whatever test that you want it to do. Okay, by just designing the output layer is what, by designing how you stack up the multi-layer DNN or convolution network. Okay. In terms of problem of statistical parameterized statistical modeling into loss design. Okay, that particular switch deep learning changes quite a bit of my ASR system. Okay, so again, repeat, starts by DNN HMMs. Okay, nothing else by it's not very special by set, right? Taking the P of O given Q now equal to P of Q given O, that P of Q given O become a frame classification problem. Just design network to predict by taking the input as my MFCC or spectrogram to predict the state numbers of my HMM. Okay, so it's 1 or 2 or 3. Okay, so usually what that's been done is you need to have an initial label, right? So you still need to do some pre-training get all those things done. And then you have this frame classification. Okay. Then people don't like it, so they will say, okay, let's make this thing merge to get a sequence of this thing out. They can use RN and CCC kind of a loss to actually be able to do this thing. Okay. Of course, with do this, you can do RNCN all the way up to language model as well. Okay. Basically drop the lexical model. Okay. So you don't have a dictionary. Okay. That tells you this phonetic sequences go to that. You let the data tells you directly. Okay. If you are able to predict intermediate representation and eventually map it to the final written character. Okay. So you don't need this explicit change into phonetic sequence and back into the character sequence. Okay. So what the deep learning community basically said, it's a data problem. So what you need is just to get a lot of data. Once you get a lot of data, you should be able to learn by learn by doing this output to character output directly without the human intervention. Okay, right? You don't need this pronunciation dictionary, people should tell you. Okay, it's like what people later on you see when people start to do DNN based things, they don't do MFCC anymore. Okay, they usually do spectrogram or some kind of filter bank. Okay, they don't do all those triangle filters and then do DCT because those operations they feel like it's man-made. Okay, if those things work, okay, you can stack the network. The network should be able to repeat that. Okay, so you should be able to learn what's right features for the spectrum. And there are also people that don't like Fourier domain as the starting point. Okay, some people like time domain as the starting point. Why do Fourier transform, then do network, right? So can you just do network directly on time waveform? Okay. There are also people that try very end-to-end, right? Taking the audio signal in just waveform, okay? Character sequence out, okay? That's the final answer. Intermediate is just a very huge network, okay? And you just train it directly on large amount of data. So that's very end-to-end network. But I think even nowadays that first transform into Fourier domain is still you cannot delete that. Okay? That's still very helpful. Okay, going directly from the time to representation and the rest of them, it's very difficult. Okay, because in time domain, I think people probably have a concept because in the Fourier domain, you drop the phase, right? You only have magnitude, so you have frequency, magnitude as input to the rest stuff. Okay, but the phasing is dropped. Okay, the phasing is the most critical issue here because you have time domain waveform. You can have different phases mapped to the same Fourier transform. Okay, so if you drop the imaginary part, but that imaginary part, if you want to properly handle that, it's going to be very difficult. Okay, and it doesn't really matter because think about it, if I delay my speech in a little bit, okay, the phase changes. The way you listen to it is still the same, but the audio sound we collect is going to be very different. People say the same word with very different phase. Okay, and that in the time domain will create a very big problem in our network currently. So not be able to learn that really end to end. So when people say end to end, usually they start from feature here. Okay. And anyways, so the rest of them you can then continue. Then the CCC loss was introduced. Then later attention loss, attention-based method, okay, has been introduced so that you can go directly from spectrogram features all the way to the character sequences. Okay, because when you model the sequence in, sequence out, okay, the sequence of characters, okay, if the sequence is very long, it should replicate what you're doing in a language model, right? Because language model essentially is just a sequence of words you're trying to find a probability. Okay, you have a very large sequence of characters, okay, and you have attention weighting that try to weight, okay, how each of the characters relate to each other. Okay, that probability essentially is repeating what the n-gram language model you're trying to do. But it's more no-brainer issue, right? Basically, all you need to do is just throw a lot of data at it, okay, and then let it learn. Once let it learn, okay, you don't need to have all this knowledge of this thing. So deep learning for the current state-of-the-art ASR system it's not becoming quite black boxy, okay, because there's no inspiration on speech production, okay, there's no inspiration on speech perception, okay. there's no need to talk about phonetic sequences. Okay, there's no need to think about dictionary, right? So if you, like I say, if I don't have this class, we just teach. We call it state-of-the-art ASR. The thing you learn, okay, you'll see is basically features, a huge network, sequence of character output, and done. Okay, that's the current state-of-the-art ASR system. Okay. It basically drops all those knowledge in between, okay, to make the current state of the art because we have so much data, okay, so much computing power that basically get rid of all these modular, okay, components. Okay. But I think this modular component actually is the key foundation on how people actually now design, okay, the current state of the art ASR system. And if you want to fix anything, you know where to fix it. Okay, the end-to-end system is very hard to fix because what that's done is basically you throw a bunch of data at it and then it learn, okay, and it does its job. Well, of course, there are other tricks that people nowadays do fine tuning instead of retraining, right? So if you things don't work on a particular data set, what you need to do is fine tune a little bit your this kind of black box ASR system. That's okay too, but then get rid of the fun of the speech. Because everything is just black box. Like throw a network at it, properly design your stuff. Okay, it's a problem of sequencing, sequence of output. So there's no special thing about speech anymore, right? So I mean that's okay too, but I think that's a trend, okay, of throwing everything in and actually take the output, let the data tell the story, okay, which is okay, but you really requires a lot of data. Okay, we're not talking about 100, 200, 300, 1,000 hours data. We're talking about like 96K, okay, 100K hours of data to be able to do what the current state-of-the-art ASR system is doing. But as I say, right, in your lifetime, before you learn how to recognize speech, okay, you're not being exposed to 100K hours of data. So the way that we humans learn to recognize speech is definitely not the way that the current state-of-the-art ASR system, deep learning system, learn how to do speech recognition. Okay, there's a very huge gap, and maybe a very very large gap that separates how machines listen to the speech and how we actually the human understand speech. So if you're interested in that, I think there's also a lot more understanding that we need to learn how human produces speech, how human recognize speech. Okay, but if you're interested in just running a very good ASR system, okay, nowadays just go to Hugging Face. One of the models, download it, run your system. Usually works. Okay, if you want to build it from scratch, you don't have a lot of data, do it like your lab, HMN, Gym, and TD and Cal, and you will see a fairly good, okay, working ASR system. 目前的写出来的。